Hello there, Mr. Sutton here, bringing you the AB Calculus 515 classwork solutions on integration by substitution with definite integrals. For this problem, we're trying to find the integral from 0 to 1 of this expression. Now, this is one where you could kind of use the brute force approach and expand this binomial, multiply by x, use the reverse power rule, and call it a day. However, I'm going to use substitution on this because I see an inner function here whose derivative is elsewhere in the problem. So I'm going to let u equal x squared plus 2. So then du equals 2x dx. And then dividing by 2x, we've got a du over 2x there. I'm also going to convert my values here, my x values, into u values. So if x equals 0, then u is going to equal 0 squared plus 2, so 2. And if x equals 1, then u is going to be 1 squared plus 2, so 3. So then I've got the integral from 2 to 3 of x, u squared, and then du over 2x. Simplifying this a little bit, the x's are going to cancel, and I can bring a 1/2 out there. Or I could leave it in there, doesn't really matter which. But now I'm going to bump this 2 up to a 3 and divide by 3. So I've got a 1/2, and then I have an evaluation box with a 1/3 u cubed in it from 2 to 3. Just to make my life a little bit easier, I'm going to bring this 1/3 out here with the 1/2 and make that a 1 over 6. And now I've got 3 cubed minus 2 cubed. And I'm just going to simplify this to match one of the answer choices. This is 27 minus 8, which is 19. So 1 over 6 times 19 is 19 over 6, giving me answer choice D. For this problem, I'm trying to get the integral from 0 to 1 of x radical 1 plus 8x squared. There's really no other way to do this than using substitution. We have an inner function whose derivative is outside the square root. So let's let u equal 1 plus 8x squared. And then if I take du, I've got, 16x dx on the other side. And dividing by 16x, I have du over that I can substitute for dx. Before I do that, though, let me turn these x values into u values. So if x is 0, then u is going to be 1 plus essentially 0, so just 1. And if x equals 1, then u is going to be 1 plus 8 times 1 squared, so that's 1 plus 8, or 9. So now I can rewrite this as the integral from 1 to 9 of x times the square root of u times du over 16x. And at this point, let me simplify a bit. So these x's cancel. I've got 1/16, and I've also got a u to the 1/2 du inside there. Now I'm going to use my reverse power rule. So this bumps up to a 3/2 exponent, and I'm going to divide that by that, so I'm multiplying by 2/3 then. So I've got 1/16, and then in my evaluation box, I've got 2/3 u to the 3/2 from 1 to 9. Now to make my life a little bit easier, I'm going to multiply this 2/3 by the 1/16 here, essentially take it outside. So that's going to give me 2 over 48, which I can reduce to 1/24. And then in a parentheses being subtracted, I've got 9 to the 3/2, which is essentially the square root of 9 cubed. And I've also got 1 to the 3/2, which is the square root of 1 cubed. So this is going to be, let's see, square root of 9 is 3. Cubing that gives me 27. This over here is going to be 1. 27 minus 1 is 26. 26 over 24 I can reduce to 13 over 12, which gives me choice B. On this problem, I'm trying to figure out the integral from 0 to pi over 4 of this crazy mess. I mean, look at this. We have e to tan, and then downstairs we've got cosine squared of x. Now, the key on this one, and it's not obvious taking a first look at it, but if you have cosine squared in the denominator, that's actually the same as having secant squared in the numerator. And now we notice we also have tan here. Hey, wait a sec. Isn't secant squared the derivative of tan? Well, it is. So you've essentially got an inner function whose derivative is elsewhere in the problem, even though it's not very obvious when we first look at this problem. So I'm going to try u substitution on this. I'm going to let my u value equal tan of x, and then the derivative of that, I've got du equals secant squared x dx. So if I divide both sides by secant squared to get dx by itself, well, secant squared is really already 1 over cosine squared. So I can just write this as cosine squared du if I multiply that by the other side there. And I still need to get these x values to turn into u values. So I'm plugging them both into the tan function to get u values out of them. If x is 0, tan of 0 is also going to be 0. So that's the u value for 0. And if x is pi over 4, well, what's the tan of pi over 4? You might remember that's 1, which is a very nice, convenient number to be working with. So writing everything now in terms of u, I've got the integral from 0 to 1 of, we're going to have e to the u over cosine squared x times cosine squared x du. And now these cosine squareds are going to neatly cancel, leaving me with e to the u du. What's the antiderivative of e to the u? Well, it's also e to the u. So I'm evaluating that from 0 to 1. So then this is going to be e to the 1 minus e to the 0. And just to match our answer choices here, that's just going to be e minus 1, which gives us choice C. On this problem, they want us to know which of the following definite integrals here has the same value as this expression. Now, they haven't really told you just in this problem stem what to do, but if you look at the answer choices, these are all expressed in terms of u. So clearly they're looking for you to do some kind of u substitution craziness with this integral. Okay, well, I do notice now that you mention it, or now that I mention it, we have an inner function here whose derivative is elsewhere in the problem. The derivative of x squared is 2x, which should interact with this x out here nicely. So I'm going to let u equal x squared, and then du is going to be 2x dx. Dividing by 2x, this gives us something we can substitute for the dx. We also need to turn these x values into u values. So if x is 0, then u is going to be 0 squared, or also 0. And if you look at all the answer choices, 0 is the lower limit of integration for all of them, so that's nothing too surprising. But now what if x is 4? Well, then u is going to be 4 squared, which is 16. So you can pretty much eliminate anything here that doesn't have 16 as your upper limit of integration. Putting it all together now, we've got integral from 0 to 16 of x times e to the u, and then we have a du over 2x. Canceling the x's here, I can write this as 1/2 0 to 16 integral of e to the u du. And I could keep going if I wanted to, but they just wanted us to find something that had the same value as this expression, and I can see this very clearly in the answer choices. This is going to be choice B. On this problem, we're trying to find the definite integral from 0 to ln 2 of all things of this crazy expression with e's in it. And I mean, just looking at the answer choices gives you a sense of how wacky this problem is. I mean, we've got inverse trig, we've got logs, we've got pies, so a little bit of everything here. Now, what I see here when I look at this is that I have an inner function, e to the x minus 1, whose derivative, e to the x, is elsewhere in the problem. So I'm thinking I'm going to try some u substitution on this one. I'm going to let u equal e to the x minus 1, because that's kind of my inner function here. And then the derivative of that, I'm going to have du equals e to the x dx. So then dx is going to be du over e to the x. All right, so far so good. We have to turn these x values into u values, though, if we're going to carry this through. So if x is 0, then u is going to be, let's see, e to the 0 minus 1. That's really 1 minus 1, which also happens to be 0. Now, what if x is ln of 2? Well, e to the ln of 2 is just 2. Subtract 1 from that, we've got 1. So ln of 2 gets converted to a u value of 1. Putting it all back together, we've got the integral from 0 to 1 of e to the x over 1 plus u squared, and then we have du over e to the x. So our e to the x's are going to cancel neatly. And I still need to figure out, though, the antiderivative of 1 over 1 plus u squared. But you might recognize this pattern. This is actually going to be arctan if you take the antiderivative. So I'm then going to have arctan of u evaluated from 0 to 1. So this is going to be arctan of 1 minus arctan of 0. So this is basically asking at what angle do I have a slope of 1? And there's lots of angles that happens at, but pi over 4 is the first one. So let's just go with that and see if we get an answer choice that matches that. Arctan of 0, they're asking at what angle do I have a slope of 0? Well, that could be either 0 or 180, but let's just go with 0 for now. So pi over 4 definitely fits this. Pi over 4 is one possible value for all of this. And if I'm really being super technical, arctan really only applies in the right half of the unit circle. So picking pi over 4 and 0 as our values really was the technically correct thing to do anyway. But anyway, this gives us answer choice C. On this problem, function f is continuous, and we're told the integral from 0 to 8 of f of u, careful how you say that, equals 6. What's the value of integral from 1 to 3 of x times f of all this stuff dx? All right, so this is a pretty clear case of needing u substitution. I mean, they have this integral with u in it, and over here we have this inner function whose derivative is elsewhere in the problem. So definitely we want to try some u substitution over here. I'm going to let u equal x squared minus 1. So then du equals 2x dx, and dx is going to be du over this 2x if I divide both sides by that. Let me also change out my limits of integration. So I'm starting with limits of 1 and 3, and those are both x values because it says dx over here. That's the tip-off. So if I have an x value of 1, plugging that in here, I'm going to get a u value of 1 squared minus 1, or 0. If x equals 3, then I'm going to have 3 squared minus 1, so 9 minus 1 is 8. So I can rewrite this as the integral from 0 to 8 of x times f of u, and then du over 2x. The x's are going to cancel, so this ends up being 1/2 times the integral from 0 to 8 of f of u du. And I'm trying to figure out the value of this thing based off of this information over here. So they actually told us the integral from 0 to 8 of f of u was 6. Well, here's the integral from 0 to 8 of f of u. This is 6. We still have this 1/2 out here, though, that we need to account for. So we're essentially doing 1/2 times the 6 that they pretty much gave us in the problem, and that comes out to 3. So choice B. For this problem, we're given an integral from 0 to k of all things of this function, and we're told it equals 1/2 ln of 4. So we want to figure out the value of k that makes this stuff happen. All right. So I'm not going to worry about this 1/2 ln of 4 just yet. I'm just going to take this definite integral over here. I'm going to get something with a k in it, and then I'll set it equal to this stuff and solve. So to integrate this, I see we have an x squared plus 4 down here. We have an x up here. I'm thinking this is really kind of like having an inner function. If you have something in the denominator, it's like having a 1 over sort of situation. So I'm going to call my u value on this one x squared plus 4, and then I'm going to try some u substitution to get to the bottom of this integral. So if u equals x squared plus 4, we can also write, if we take the derivative, du equals 2x dx, and then I'll divide by 2x to get dx by itself. I'm also going to swap out my u values, or my x values rather, for u values. So if x is 0, then u is going to be 0 squared plus 4, which is 4. And here's where it gets interesting. If x is k, then u is going to be k squared plus 4. All right, plugging it back in. We've got the integral from 4 to k squared plus 4. That whole k squared plus 4 is the upper limit of integration. And then inside we have x over u times du over 2x. Let's simplify this a bit. We can cancel those x's and call this essentially 1/2 times all this. And we have a u to the negative 1, or 1 over u, however you want to write that. what is the antiderivative of 1 over u? Well, that's going to be ln of absolute value of u. We still have this 1/2, though, playing around out there. So we have 1/2, and in my evaluation box, I've got ln of absolute value of u from 4 to k squared plus 4. Let me go ahead and plug these in now. So I've got the 1/2 out here, and inside my parentheses being subtracted, I've got ln of k squared plus 4. And now when I do this, I actually can drop the absolute value, which I'm going to need to do to solve this anyway, because k squared plus 4 is guaranteed to be positive. I mean, even if you could have negative k values, squaring them is going to make them positive. Adding 4 is just going to make it more positive. And look what they said up here. K is positive. So any way you look at it, we can just write this as ln of parentheses k squared plus 4. And we can also write just ln of 4 with no absolute value because, well, 4 is positive. So there's no need to change that. Now, this expression, where do we go from here? This is where we remember, oh yeah, this integral that I got all this from equals 1/2 ln of 4. So I'm going to put this down here and actually create an equation now that I can solve for k. All right, so going through the algebra on this one, I can definitely cancel out these 1/2s. And while I'm taking that important step, I'm also going to combine these logs on the left side. So if you're subtracting logs, you can divide the things inside. So I can write this whole left side as ln of k squared plus 4 over 4 inside the logarithm. And again, I canceled out those 1/2s, so those just disappear. Next step, I'm going to cancel out some more things. These both have an ln, so I can drop the ln's. So then I have k squared plus 4 over 4 equals 4. And going a little bit further here, I can multiply both sides by 4 to get 16. Subtracting 4 gives me 12. K squared equals 12. Well, it's time to square root. So we end up with k equals plus or minus radical 12. But they told us that k was positive, so we're just going to have positive radical 12 then, which gives us choice D.